Hello, my dear students. Welcome to IKSR chemistry classes. Here we are in lecture number 5 on nuclear chemistry. In this video, we will discuss N by P ratio and nuclear stability. Let us first of all we see what is neutron-proton, that is N by P ratio. The ratio of the number of neutrons and the number of protons present in the nucleus of an atom is called its N by P ratio. Let us illustrate it taking example of C14 isotope of carbon. It contains 6 protons, this one, and 14 minus 6, that is 8 neutrons, and therefore its N by P ratio will be 8 by 6, that is 1.33. N by P ratio of some other nuclei. These are some isotopes. C12 contains 6 protons and 6 neutrons in the nucleus. Hence, its N by P ratio will be 6 by 6, that is 1. O16 contains 8 protons and 8 neutrons, and accordingly, its N by P ratio will be 8 by 8, that is 1. Ca40 contains 20 protons and 20 neutrons in the nucleus, and hence its N by P ratio will be 20 divided by 20, and it is also equal to 1. Beryllium 7 contains 4 protons in the nucleus and 7 minus 4, that is 3 neutrons in the nucleus. Its N by P ratio will be 3 by 4, that is 0.75. On the other hand, uranium 92 238 contains 92 protons and 238 minus 92, that is 146 neutrons in the N by ratio in the nucleus, and hence its N by P ratio will be 146 divided by 92, and it will be equal to 1.59. These are the N by P ratios of some common isotopes. N by P ratio and nuclear stability. The stability of a nucleus depends upon its neutron-proton ratio. Up to atomic number 20, the most stable nucleus generally exists, not necessarily. Up to atomic number 20, the most stable nucleus generally exists when it contains same number of neutrons and protons, that is the N by P ratio is 1. Up to atomic number 20. A stable nucleus generally exists when its N by P ratio is equal to 1. After atomic number 20, the addition of neutron to the nucleus is preferred to the addition of proton due to following two reasons. Up to atomic number 20, a stable nucleus exists when it contains same number of neutrons and protons, that is N by P ratio is equal to 1. But after atomic number 20, the addition of neutron to the nucleus is preferred to the addition of proton. After atomic number 20, the addition of neutron to the nucleus is preferred to the addition of proton due to following two reasons. The addition of neutral neutron to the nucleus does not increase the electrostatic repulsive force. The addition of the neutron, which is neutral in nature, to the nucleus does not increase the electrostatic repulsive force. But the addition of neutron to the nucleus increases the attractive exchange force between adjacent neutron-neutron and neutron-proton pairs. The addition of neutron to the nucleus increases the attractive force, increases the attractive exchange force without increasing the repulsive electrostatic force. Therefore, after atomic number 20, the addition of neutron to the nucleus is preferred to the addition of proton. And what are its consequences? If we plot N by P ratio against the atomic number for stable isotopes, it remains horizontal at N by P equals to 1 up to atomic number 20. Let us see it again. If we plot N by P ratio against atomic number for stable isotopes, the curve remains horizontal at N by P equals to 1 up to atomic number 20. Thereafter, that is after atomic number 20, the N by P ratio goes on increasing with increase in atomic number and attains a maximum value of about 1.6 at the atomic number 92 of uranium. After atomic number 20, the N by P ratio goes on increasing with increase in atomic number because the addition of neutron to the nucleus is preferred to the addition of proton, because the addition of neutron increases the attractive exchange force without increasing the repulsive electrostatic force. At this point, that is at N by P ratio equals to 1.6, the nucleus becomes so large that it undergoes a spontaneous fission. If the size of nucleus becomes very large, and it happens at N by P ratio equals to 1.6, the nucleus becomes unstable and it undergoes a spontaneous fission. If we plot N by P ratio against the atomic number for stable isotopes, the N by P ratio remains constant at 1 up to atomic number 20, and after atomic number 20, the N by P ratio goes on increasing with increase in atomic number and it attains a maximum value of 1.6 for a stable nucleus at the case of uranium 92 atomic number and with mass number 238. The N by P ratio of U238 is 1.59 as we have calculated earlier. But the nucleus of uranium is so large at N by P ratio equals to 1.6 that it undergoes a spontaneous fission. Now, a stability curve. The curve obtained by plotting N by P ratio against the atomic number of stable isotopes is called a stability curve. If the N by P ratio of stable isotopes is plotted against their atomic number, the curve obtained is called a stability curve, as shown on the right hand side. N by P ratio of stable isotopes is plotted against atomic number, and the curve obtained is of this type. Up to atomic number 20, the N by P ratio remains constant and it is equal to 1. After atomic number 20, the N by P ratio goes on increasing slowly and its maximum value is equal to 1.6 at the in the case of U-238, and its nucleus becomes so large that it undergoes a spontaneous fission. This curve is called a stability curve. Let us see the positions of some isotopes in this plot. Beryllium 7 has N by P ratio equal to 0.75. C12 has N by P ratio equal to 1. Ca40 also has N by P ratio equal to 1, but C14 has N by P ratio equal to 1.33. The isotopes having N by P ratio on the or near the stability curve has a stable nucleus. The isotopes whose N by P ratio lies on the stability curve or near the stability curve have a stable nucleus and they are non-radioactive. On the other hand, the isotopes having position much below or much above the stability curve has unstable nucleus and such isotopes are radioactive. On the other hand, the isotope having position much above or much below the stability curve has unstable nucleus. It undergoes nuclear disintegration in such a way that it may come closer to the stability curve. The isotopes having position on the stability curve or near the stability curve have a stable nucleus and they are non-radioactive. On the other hand, the isotopes having position much above or much below the stability curve have unstable nucleus and they undergo nuclear disintegration in such a way that they may come closer to the stability curve. Let us see an example. C14 has N by P ratio 1.33 as we have seen earlier, and its position on the stability curve its position in the graph is much above the stability curve and it is radioactive. It is beta active. It emits a beta particle. Beta particle is nothing but an electron, and C14 has N by P ratio equal to 1.33. Its position is much above the stability curve. It emits beta particle. As a result, N14 is formed. It is a nuclear reaction which is balanced with respect to charge as well as mass number. The charge on the left hand side is 6 and the charge on the right hand side is also 6. 7 minus 1. The charge is balanced on both the sides. Similarly, the mass number on the left hand side is 14 and on the right hand side the mass number is again 14. 14 plus 0. Thus, this nuclear reaction is balanced with respect to charge as well as mass number. C14 is radioactive. Its position is much above the stability curve. It emits a beta particle forming N14 whose N by P ratio is equal to 1. Thus, C14 undergoes nuclear disintegration emitting beta particle in such a way that its position comes closer to the stability curve. On the other hand, B7 has N by P ratio 0.75, 3 by 4. Its position is much below the stability curve. it emits a positron forming lithium-7. It is also a nuclear reaction. The charge on the left hand side is 4 and on the right hand side it is also equal to 4. 3 plus 1. The mass number on the left hand side is 7 and on the right hand side the mass number is again 7. Thus this nuclear reaction is also balanced with respect to charge as well as mass number. Positron is the anti-particle of beta particle. Positron is the anti-particle of beta particle. If two particles annihilate each other and their masses are transformed into energy in accordance with E equals to mc square, then two particles are called antiparticles. If two particles annihilate each other and their masses are transformed into energy in accordance with E equals to mc square, they are said to be antiparticles. Here beta particle and positron are antiparticles. These have same mass but opposite charges. Beryllium-7 is radioactive. Its N by P ratio is 0.75, which is much below the stability curve. It emits a positron forming lithium-7, whose N by P ratio is equal to 1.33. Thus, the N by P ratio of beryllium-7 increases on emitting positron. Now, the time for self-assessment. During beta emission, the proton is transformed into neutron. The neutron is transformed into proton. N by P ratio increases. None of these. Let us try to solve this problem taking example of beta emission. C14 emits beta particle as we have seen earlier. C14 contains 8 neutrons and 6 protons. Its N by P ratio is equal to 1.3. N14 contains 7 neutrons and 7 protons. Its N by P ratio is equal to 1. It can be seen that during beta particle emission, the number of neutrons decreases from 8 to 7, while the number of protons increases from 6 to 7. It means one neutron is transformed into proton as follows. This neutron is transformed into proton during beta emission. As a result, the number of neutrons decreases by 1 unit, while the number of protons increases by 1 unit. And the correct answer is neutron is transformed into proton. N by P ratio here decreases, while this option is not correct. N by P ratio increases. Therefore, the answer of this question will be proton is transformed into neutron. There is another question for self-assessment. During positron emission, proton is transformed into neutron, neutron is transformed into proton, N by P ratio decreases. None of these. Let us try to solve this problem also taking example of positron emission as we have seen earlier. Be7 emits a positron forming Li7. B7 contains 3 neutrons and 4 protons. Its N by P ratio will be 3 by 4, that is 0.75. Lithium 7 contains 4 neutrons and 3 protons. Its N by P ratio will be equal to 1.33. Here we can see that the number of neutrons increases by 1 unit, while the number of protons decreases by 1 unit. That is, one proton is transformed into neutron as follows. This proton is transformed into neutron during positron emission. This is a nuclear reaction and it should be balanced with respect to charge as well as mass number. One charge is present on the left hand side and on the right hand side the charge is also +1. The mass number is 1 and here also the mass number is equal to 1. During positron emission, the proton is transformed into neutron and therefore the correct answer is A. Now the time for another self-assessment. During alpha emission from the nucleus, the alpha particle contains 2 protons and 2 neutrons. Alpha particle is nothing but a bundle of 2 protons and 2 neutrons. An alpha particle is emitted from the nucleus. It means the nucleus emits 2 neutrons and 2 protons. A nucleus emits alpha particle means it emits 2 neutrons and 2 protons. And during the alpha emission from the nucleus, proton is transformed into neutron, neutron is transformed into proton, N by P ratio increases, N by P ratio decreases, or N by P ratio remains constant. 2 neutrons and 2 protons are emitted during alpha emission. What will be the effect on N by P ratio? Increases, decreases, or remains constant? Let us illustrate it taking an example of alpha emission. Uranium-238 emits an alpha particle forming the nucleus of thorium-234. This nuclear reaction should also be balanced with respect to charge as well as mass number. The charge on the left hand side is 92 and on the right hand side the charge is 90 plus 2, that is 92. The mass number is 238 and on the right hand side 234 plus 4. This nuclear reaction is balanced with respect to charge as well as mass. U-238 contains 146 neutrons, 238 minus 92 and 92 protons. Its N by P ratio is 1.59. On the other hand, thorium-234 contains 144 neutrons and 90 protons. Its N by P ratio 144 divided by 90 will be 1.6. It is obvious that during alpha particle emission, the N by P ratio increases and therefore the correct answer will be C. During alpha emission, 2 neutrons and 2 protons are emitted. Despite it, the N by P ratio increases. The time for a homework. The beta particle is nothing but electron. Beta particle is nothing but electron. It is emitted from the innermost orbit of atom, the outermost orbit of atom, the nucleus of atom, or none of these. Solve this problem and submit your answer in the classroom. Thank you for watching the video with concentration.